This episode is brought to you by Brilliant. Since the dawn of computing, a single construct has served as the focal point of this transformational technology, the algorithm. By definition, an algorithm is simply a finite sequence of instructions, structured to solve a problem. In modern digital computers, these instructions resolve down to the manipulation of information represented by distinct binary states. These bits may be abstractly represented by various physical phenomena such as mechanical, optical, magnetic, or electric methods, and the process by which the binary information is manipulated is also similarly versatile, with semiconductors being the most prolific medium of these machines. Fundamentally, a binary computer moves individual bits of data through a handful of logic gate types. These gates have clearly defined binary outputs in response to binary inputs, and by combining layers of these gates into massive networks, a deterministic processing machine can be created. A CPU, for example, is a complex manifestation of just such a machine. The flow and manipulation of digital information is abstract by nature. The underlying physical medium only determines the packaging, performance, cost, and practicality of its use, but not its inherent behavior. In digital computing, binary information moves through a processing machine in discrete steps of time. The duration of these steps are limited by the speed at which logic states can be physically changed as information propagates throughout the underlying logic gate network, inherently making time a computing resource. In addition, the capacity of a processing machine to temporarily store and manipulate information within itself permits even more elaborate forms of processing to be done. This, in effect, makes memory another fundamental computing resource. Because any series of instructions tasked to solve a problem are confined to the bounds of computing resources, algorithms designed for digital computers can be classified by their use of these resources as they scale. This is known as an algorithm's complexity. The most time-efficient algorithms are categorized as constant time. Constant time algorithms always take the same amount of time to execute regardless of the size of the input. An example of such an algorithm would be one that determines if a number is even or odd. To accomplish this, only the last digit of a number needs to be examined, no matter how large it is. Because only one number is always examined for any input size, the solution is always produced in one fixed duration of time. Algorithms can also scale in compute time at a constant rate. These are known as linear time algorithms, and they execute at a rate that is directly correlated to the size of the algorithm's input. This characteristic becomes obvious with a basic addition algorithm. The sequence starts with the rightmost digit pairs being added. From here, the algorithm then moves left to the next pair of digits, adding any carryover, and the process is repeated until no digits are left. Because the number of steps and inherently the execution time is directly determined by the size of the number inputs, the algorithm scales linearly in time. Constant and linear time algorithms generally scale to practical execution times in common use cases. However, one category of algorithm in particular suffers from the characteristic of quickly becoming impractical as it grows. Let's look at an algorithm that must be designed to search for a 4-digit numeric code. This algorithm calls upon another constant time algorithm that will validate if the numeric code is correct, signaling the end of the search. With no prior information to go on, the search algorithm must cycle through every single 4-digit permutation until a valid code is found. This is known as the brute force method, and for a 4-digit code, up to 10,000 codes must be tested by the validation call, with the code being found on average by the 5,000th try. While this isn't particularly noteworthy for modern processors, a problem soon arises as this brute force algorithm is forced to deal with larger codes. With a 5-digit code, 100,000 combinations are now possible. At 6, it becomes 1 million. With each digit added to the code, the number of possible combinations increases tenfold from the previous number of combinations. Since testing each combination requires a constant period of time to execute, the overall time to execute the brute force algorithm rises exponentially as digits are added to the code. This is known as an exponential time algorithm, and they pose a huge problem for traditional computers, as the execution time can quickly grow to an impractical level as input size increases. Problems that exhibit this characteristic are known as intractable. They can in theory be solved, but require far too much time or memory to practically arrive at a solution with current computing technology. While intractable problems can be viewed as a computational hindrance or a limitation, their nature also lends themselves well for security purposes, such as in the case of asymmetric encryption. The RSA algorithm, for example, forms the basis for much of the encryption we use, including the encryption mechanism that secures the internet. At its core, RSA is secured by the fact that factorizing a large number to find its two large prime number factors is an intractable problem. This problem is so difficult for modern computers that in 2020, it took a supercomputer the equivalent of almost 2,500 years per CPU core to find the prime factors for a 250-digit number. At present, to threaten the most commonly used RSA encryption, the ability to factorize a 617-digit number is needed. It's estimated that at present, it would take almost 3 trillion years per CPU core to accomplish this. In the early 20th century, physicists began to develop new ways to describe the seemingly unintuitive behavior of the most elemental interactions in physics. Called quantum mechanics, these concepts revealed an entirely new perspective on how reality functions at the most fundamental levels of observation. By 1980, physicist Paul Benioff would go on to propose applying the principles of quantum mechanics to computation. Physicist Richard Feynman would soon suggest that such a computer had the potential to simulate things a classical computer could not feasibly do. And by 1986, he would propose the earliest concepts for quantum computational circuits. From these initial conjectures, computer scientists soon discovered that, in theory, they could exploit this newly discovered offshoot of quantum mechanics to create more efficient algorithms. Problems such as factorization that were believed to be intractable for conventional computers now had the potential to be completely manageable with a quantum computer. Much like how digital systems use bits to express their fundamental unit of information, quantum computers use an analog called a qubit. However, a qubit behaves dramatically different than a traditional digital bit. In traditional bits, only two discrete states exist, 1 and 0. These states are generally defined by two clearly distinguishable physical properties. In the case of semiconductors, voltage levels are used. When a bit signal is applied to a digital logic gate, typically some form of active switching occurs where an input state triggers either an activation or deactivation of one or more internal switches to produce a clearly defined output state. A key tenet of digital logic is that the information is always clearly defined, measurable, and their logic gates are deterministic. Quantum computing, by contrast, is probabilistic. While qubits can be measured as two discrete states like digital logic, they exist in a natural state known as a coherent superposition, where no clear state can be inherently assigned to it. Unlike digital logic, the act of measuring a qubit destroys its coherence, irrevocably collapsing its superposition state to a classically digital one. A key difference in the value of this measured quantum state when compared to a classical digital bit is that it is not deterministic, but rather based on probability. It is the manipulation of these probabilities as they move between qubits that form the basis for quantum computing. Qubits are physically represented by quantum phenomena such as the spin-up, spin-down levels of an electron, or the vertical-horizontal polarization of a single photon, and they operate entirely by their natural quantum mechanical interactions. How the probabilities of qubit states are modified when interacted with comes down to the quantum principle of phase. A qubit possesses an inherent phase component, and with this characteristic of a wave, a qubit's phase can interfere either constructively or destructively to modify its probability magnitudes within an interaction. A classical analogy for the use of interference to produce desired information can be found in noise-canceling headphones. These devices create an inverse electrical signal from a microphone sampling ambient sounds, and mixes it with the intended audio signal. The interference interaction of the two signals results in a signal that mostly cancels out ambient sounds as it converts back into a pressure wave and enters the ears. In effect, a quantum program is a group of qubits configured with probability-modifying elements in between to form a large interference network. This network in concept, when tuned, should resolve to a high probability of a solution to the problem for which the network was created for. It's important to note that the mechanisms of these interactions are never observable and are only defined by mathematical models, as attempting to directly measure them would cause the network to decohere into a single state. Measurement can only occur at strategic points in the network where the answer lies within the collapsed state. In addition, because of the probabilistic nature of the process and its inherent susceptibility to noise, the final measurement must be made at minimum thousands of times in order to build a statistical profile of the likely outcome of the network. Qubits possess no intuitive analog to our classical world experience. Their characteristics and behavior, like much of quantum mechanics, are modeled using complex numbers. However, most of these properties can be visually represented using a geometric construct known as a Bloch sphere. A Bloch sphere visualizes a qubit's magnitude and phase using a vector within a sphere. In this representation, the two classical bit states are located at the top and bottom poles where the probabilities become certainty, while the remaining surface represents probabilistic quantum states, with the equator being a pure qubit state where either classical bit state is possible. The phase component is also represented by the hemispheres at each side of the x-axis of the Bloch sphere. When a measurement is made on a qubit, it decoheres to one of the polar definitive state levels based on its probability magnitude, collapsing any positions of uncertainty in the process. Much like how classical digital bits have no computational value without digital logic gates, quantum computers employ quantum logic gates on qubits to operate. Quantum gates are the fundamental blocks of how information is manipulated within a quantum circuit. However, unlike their digital counterparts, a quantum gate modifies a qubit's probability magnitude and its phase component, not any direct values. Quantum gates are categorized by their pattern of operation and the number of qubits they operate on. Among them, Pauli gates are the most intuitive. Pauli gates come in three variations: Pauli X, Y, and Z. The X and Y gate in particular behave exactly like a digital NOT gate. Operating on a single qubit, they invert the value of a 1 or 0 state. However, on a Bloch sphere, their quantum behavior is fully expressed. Pauli gates rotate the vector that represents a qubit's probability magnitude and phase 180 degrees around the respective X, Y, and Z axis of its Bloch sphere. For the X and Y gate, this effectively inverts the probability magnitude of the qubit, while the Z gate only inverts its phase component. It's important to note that phase changes caused by Pauli gate operations determine how the qubit will interact with certain types of other gates. Some quantum gates have no classic digital equivalent. The Hadamard gate, or H gate, is one of the most important unary quantum gates, and it exhibits this quantum uniqueness. A Hadamard gate, in effect, can move a binary state level in and out of superposition. Take a qubit at state level 1, for example. Applying a Hadamard gate to it results in a superposition state. If a second Hadamard gate is applied directly after, the superposition is returned back to its previous state of 1. The Hadamard gate's memory of the qubit's previous state is derived from the qubit's phase component. If a measurement is made between two Hadamard gates, the collapsing of the first Hadamard superposition would destroy this information, making the second Hadamard gate's effect only applicable to the collapsed state of the measurement. When visualized on the Bloch sphere, a Hadamard gate simply mirrors a qubit's vector through a diagonal slice through the Bloch sphere that is defined by z equals x. From this, the function of superposition reversibility through phase becomes clearer. In addition to the Pauli gates and the Hadamard gate, two other fundamental gates known as the S gate and T gates are common to most quantum computing models. The S and T gates are known as phase gates, as they only affect the phase component of a qubit at 90 degrees and 45 degrees respectively. From these 6 fundamental unary gates, composite gates can be created that allow for both rotation or phase shifting at arbitrary angles. These are called the Rx, Ry, and Rz gates for rotation, and the R phi phase shift gate. It should be noted that both the RZ and R phi both rotate phase, but R phi only operates on the one-state level region of a qubit. Much like their digital counterpart, quantum computing requires gates that operate on multiple bits in order to accomplish useful computation. However, in contrast to a classical digital logic gate, a multi-qubit quantum operation is done completely without measurement. This nuanced difference results in the involved qubits losing their distinctiveness in the operation. They become entangled. Entanglement is a strange and unique characteristic of quantum mechanics, and alongside superposition, they form the two key tenets of quantum computing. When two qubits become entangled, they no longer have individual independent states. They become two components of one composite, irreducible superposition, and one cannot be described without the other. Entanglement is accomplished using a gate type known as a control gate. Control gates trigger a correlation change to a target qubit when a state condition of the control qubit is met. These gates introduce conditional logic into quantum computing, but when combined with the properties of entanglement, the true power of quantum computing becomes apparent. The most important of these gates is known as the control NOT gate, or C0 gate. A C0 gate causes a state flip of the target qubit, much like a digital NOT gate, when the control qubit is at a state level of 1. In addition, an entanglement is also created between both qubits, creating a persistent correlation. The implication of this is that if both qubits are measured, the measurement will always produce a correlated result. The properties of entanglement can be easily observed when a Hadamard gate is applied to a qubit, and it is connected to a second qubit via a C0 gate. Because the control qubit is placed in a superposition by the Hadamard gate, the correlation created by entanglement through the C0 gate also places the target qubit into a superposition. This is known as a Bell state, and it makes either single qubit state indeterminate. When the control or target qubit state is collapsed by measurement, the other qubit state is always guaranteed to be correlated by the C0 operation. If both qubits are measured, both measurements will always collapse into a correlated result. C0 gates are used to create other composite control gates, such as the CC0 gate or Toffoli gate, which requires two control qubits at a 1 state to invert the target qubit, the swap gate, which swaps two qubit states, and the CZ gate, which performs a phase flip similar to a R5 gate when the control qubit is at a 1 state. While far more complex composite control gates can be created, these are the simplest and most common. The quantum entanglement at the core of these gates has a curious property that imparts tremendous computational power to quantum computing. They transmit their correlations faster than the speed of light. In fact, the most recent experiments have placed a minimum speed for entanglement at around 3 trillion meters per second, or about 10 million times faster than light. In theory, massive quantities of qubits can be entangled together and interacted with for the purposes of computation with no negligible increase in processing time. When combined with the fact that a qubit is continuous by nature and has infinite states, this quickly scales up to a magnitude of information processing that rapidly surpasses traditional computing. For comparison, using a modern computer, even just coarsely simulating a 20-qubit operation can take up to 20 seconds, with the compute time increasing exponentially with each additional qubit added. On real qubits, the same operation happens at the scale of nanoseconds. In part 2, we'll look at the nature of designing quantum algorithms, their application, and the challenges associated with creating them. We'll also explore the physical limitations of quantum computing and how its current state of development aligns with theoretical expectations. For this video, I've purposely chosen conceptualization over math to introduce this incredible new frontier of computing. However, quantum computing does require an understanding of the mathematically abstract to fully appreciate its potential. And with Brilliant, building a solid mathematical foundation to fully grasp these concepts has never been easier. Brilliant is my go-to tool for diving headfirst into learning a new concept. It's a website and app built off the principle of active problem solving. Because to truly learn something, it takes more than just watching it. You have to experience it. With this in mind, Brilliant has been tirelessly revamping their courses to introduce even more interactivity, and with their recently updated Introduction to Probability course, you'll be able to examine and explore the power of quantifying uncertainty. In this course, you'll bypass the calculus and use a simulation system that lets you apply the rules of probability as you learn them, without being bogged down by difficult calculations, all while developing skills aimed at modeling real-world scenarios. With Brilliant, you learn in depth and at your own pace. It's not about memorizing or regurgitating facts. You simply pick a course you're interested in and get started. If you feel stuck or made a mistake, an explanation is always available to help you through the learning process. If you'd like to try out Brilliant and start learning STEM for free, click the link in the description below or visit brilliant.org/newmind, and the first 200 of you will get 20% off an annual premium subscription.